So what I want to do is show you some work of basically the accuracy and precision of perceiving the gaze of a virtual agent in virtual reality. Now, I already heard that some people believe that, well, gaze is not so important, but we can do a lot of stuff with gaze. For example, we can provide you a hint on what is the next correct card in a memory game. So effectively, that's cheating. That's what Hemminghouse and Kopf 2017 did. Or we can provide instructions on how to sort these rods into specific sorts of containers using gaze. And Stauter and Crocker went one step further and showed that you can override an explicit verbal reference to one of these objects by just looking at another one. The ability to identify the gaze target of our interlocutor actually enables us to understand which object will become relevant to them. And thereby we can predict their intentions. And if you're thinking about managing the flow in a conversation, you can select the next speaker, not necessarily by pointing at them, but we're just looking at them. So in all these cases, we use gaze in a sense of like a pointing gesture, like in creating a reference, but just for our visual system. And the ability to read this cue has been argued to be fundamental in our ability to join a social interaction. And in fact, Tomasello and Carpenter went a step further and said, well, that's actually fundamental to our development as such. So if you're now thinking about creating a virtual character, an agent, that is supposed to be coherent and consistent, you do have to get the gaze right. At least to the extent that you're not producing a mismatch between what you're saying and what you're doing with that agent. Now you probably realize that all the examples that I've shown you were either real humans, like in the real world, or robots, and that we are in a virtual agents conference. So we should move into pictorial space. And pictorial space is typically 2D, and we already know that 2D is quite difficult because we have to deal with a lot of effects, like perhaps the most prominent is the Mona Lisa effect. That is, you're either selecting everybody as the next speaker or nobody. We also have like a bit more quirky stuff, so the presence or the absence of this nose in that row of cubes makes us perceive the rotation differently, even though the cubes are perfectly identical apart from that nose. And having a large nose myself, I know what I'm talking about. Okay, so here we are. We are wondering if we're using virtual reality, do we have to deal with these effects that we see in pictorial space, because actually we're talking about a depiction, or are we closer to what we see with real humans? So we went actually to a very simple virtual reality. It's just the room, it's just that table, and our virtual agent Mark here created from Autodesk, so it's not as super fancy as some of the agents that you have seen here already. And we've replaced the eyes with a very high resolution version of that. Now the task for the participants is comparably simple. Our agent Mark would look at one position on this table surface, and the participant would then go collect this little blue cube over there with the controller and position it on the table such that we can measure where they believe that Mark was gazing on. So what we measure then is the position of this cube on the table, and we do a lot of computation in terms of how they perceive the vertical and horizontal visual angles. Now, before I actually show you these computations, we should look at the participant's perspective. And you already see this kind of suggestively empty chair. And so we positioned our participants right in that chair. And it was really nice that we matched this with a real chair in the real world at that very same position. So it was very generous of us. I always feel. Okay, and this is a really scruffy video screenshot recording, so it's not very fancy, but you can see what's going on. Participant collects this blue cube and positions it on the table, and then the next trial will start. And again, you collect this blue cube and you position it on the table. You see the message here. But this green thing that is moving up and down all the time, that's basically to block the view on how we rotate the agent to the next target. I mean, there's nothing wrong with seeing that. I mean, there's no secret in that, but it makes it more comparable to studies that we have seen with human lookers. So we just block that view of the rotation because how the thing moves could provide some additional information. Okay, so these are, that's not all of the results, there's a bit more to come, but this is a plot of the table surface. So you're just looking from the top down onto this table, And so the virtual agent would be seated on the top end of that slide, and our participants would be seated here in the bottom. And these 5 black dots, these are our gaze targets. And you can see this central spot there. This is really the central point. It's halfway between the agent and the participant. It's right in the center of the table surface in both dimensions. And then we went 15 and 30 centimeters to the left and to the right. So that means we have 5 gaze targets. We presented them 20 times in random order with 10 participants. That gives us 1,000 points of measurements. And I want to show you all of them, but don't panic. It's fine. It's fine. So what you can do is now you can compute the vertical angle and the horizontal angle. And I've highlighted that procedure in black for one participant. So you can see these kind of arc-shaped lines. That's the vertical angle of looking down to the table surface, and you get this kind of circular shape on the table surface, so it makes sense. And you can see the other lines that look like rays going out of the virtual agent, and that's the horizontal angle. And the intersection of those 2 lines, that's basically the central tendency for one participant at one gaze target. Now, you probably guessed it, but we arranged these points from left to right, so that means we're interested in the horizontal angle, and I'm just going to focus on that for a while. The first thing that you see is, when you look at this central point, we get a really nice accuracy and precision. All these points are kind of overlapping, that's actually very encouraging. The second thing to see is that we are losing both as we move further to the sides. In fact, we get a greater variance. And if you look at that, and that's point number 3 to see, if you look at these lines, they're all further to the side than they should be. So in other words, we get an overestimation of the horizontal angle, and that is in both directions respectively. Now if you go through that, you do all the computations and so on and so forth, what you will find is that there's an overestimation coefficient for each participant. Right? So we have to multiply the angle that we actually produce, true angle, with that overestimation coefficient, and we end up with that central tendency. Now this coefficient is bound to the individual, so there are differences between the participants. Now what happens when multiplying in a large angle? Well, we see this increasing spread as we are further out, but if you're multiplying in something like a 0, like the symmetrical one, we're not expecting anything, so that's this beautiful accuracy and precision that we can see over here. Now, one of the consequences is that if you have 2 objects in your virtual world, and you want to produce a coherent reference to one of them, that's literally straightforward if they're central. But you have to put them further and further apart as you're moving further out in order to achieve an agreement between participants. Okay, so if we now compare this to what we know from human lookers, well, first of all, we know that if we're trying to understand where a human looker is looking at, we don't have any systematic offsets. We have a nice precision accuracy at the central position. That's precisely what we have seen. We also know that we overestimate the visual angle as we're going further out to the sides. And again, that's something that we have seen. And we also know that the variance increases as the visual angle increases. Again, that's something that we have seen. What we did not know, though, is that this increase in variance is by some large extent driven by these individual differences. So by these coefficients that are bound to the single participant and differ between them. Okay. Now, these positions, that's not the only thing that we have measured. We have also looked at where our participants look in the virtual world. So whether they look at our agent, whether they look at the table surface, or at the controller and the cube and so on and so forth. Now, in order to make some sense of these measurements, you do want to normalize the duration of each trial, and then at each time slice you want to plot the distribution of these gaze targets, right? And you can see what is going on. That kind of makes sense. So you have to look at the response times. This is what I did. Fair enough. So what you see is the distribution of response times for each of the participants. They are not hugely surprising. You get these large peaks, and then there's some slow outliers towards the end, which is perfectly fine. They're not hugely different. But what is different is the scale. So this chap over here used 4 seconds on average, and that guy more than 10. So again, we have huge individual differences, but also astonishing consistency within participants. That in mind, we can now look at these distributions of the gaze targets. Before we look at the color of these lines, I just want to say that the peaks are pretty high, right? So we're looking at things like more than 80%. What that means is that this participant looked at the precisely same target object at the precisely same moment in time for more than 80 out of these 100 trials. So that's an astonishing kind of consistency within the participants. Let's look at these two people and the line colors. So let's start with number 4 here. That's our fast one. She started off with the green line. That's basically the table. That's the controller, and this token's perhaps just picking up the thing. You look at this red line. That's the agent. So you can identify where to go. You see this small drop towards the end, and that's perhaps just checking where you are. Now the person next to that went way more up and down. There's much more looking forth and back, but between the up and down. But again, it's very consistent. So these participants really went through 100 trials and they did the same thing over and over again, which is kind of remarkable in a sense. So to summarize and to conclude, really, we have seen that our virtual agents are perceived pretty much like real humans. So we have seen all these properties that we already know. But when we look deeper into what we have measured, we have seen that this overestimation, the overestimation coefficient, is bound to the individual. We've also seen that response times are very consistent within individuals, but they differ quite a bit between them, actually almost factor 3. We've also seen that participants perform the task very consistently, but again, each participant did it quite differently, but very consistently. So that means we have individuals that are very consistent, but we have large individual differences. So if you're creating a virtual agent, you can't just go and average across all the participants that you have, because what you end up with is an unobserved chimera. It's something like a mixture of everyone that doesn't really exist in the world. So if you want something that is coherent, consistent, you probably go with the behavior of one participant. That has also been shown for gestures by Backman-Kopp and ISO. With that, I should conclude and of course refer to the students that did the actual work, as you can see us all gazing to one side. Thank you.
Any questions? I'm going to be very efficient now.
To what extent you think your results might be dependent on the particular character you used? If you have a different head shape or different resolution?
Yeah, we're actually wondering about resolutions and so on and so forth. What is a bit encouraging in that we generalize is that we have seen something in a similar magnitude actually in terms of standard deviations of the size of the overestimation with real humans. What was different was that the standard deviations were slightly larger. And I would attribute that very much to the resolution of the HTC Vive that we were using. But by and large, it was encouraging in the sense that it really mirrored something that we know.
Another, so of course, the perspective of the participant is flexible. Basically, they can move around in the environment. So maybe, did you notice that maybe some people, as they were about to place the object, they were actually leaning in and then perhaps changing their mind? Or do you feel like the position of their own head could possibly influence the point that they picked?
Yeah. We thought about using like one of these chin rests that you kind of do to fix the participant, but we kind of refrained from that because it's kind of natural to move around a little bit, and if that's something that helps them, fair enough. But to all of that I've seen, that there's not much help in that. So they might do that now. Participants will kind of lean forward and try to get closer and closer to the thing, but it doesn't help that much. So they were kind of stuck, and even if you're wondering about something like a learning effect over time, nothing. So you can do it 100 times, you can do it 1,000 times, as a flat line. Oh, okay.
Any other questions?
Actually, I have a very small question. I was wondering how you confirm your parameters. Like, if you look aside, you actually need to fulfill your hand. So you need to determine like which angle of the eyes can trigger the rotation of the hand. So.
Right. There is a paper by and Kopp that's basically the default model for this kind of thing. Their approximation is, roughly speaking, you rotate the head about 1/3 of the way, and then the eye is just precisely positioned on the target spot. And then you kind of know how far you went, and we just use the sum of head and eye rotation.
That's thanks, Sebastian.